Looks like we're finally live. Hello everyone and welcome to yet another recreational programming session. Who built it? We shouldn't expect that shit to happen. Yeah. It's unexpected every time. So let's make a little bit of an announcement on our Discord server and officially start the stream. So a red circle live on Twitch. Alright, and what we're doing on Twitch Today we are making a compiler, as usual. So, and today specifically, we're trying to speed up the type checking process, right? I'm not 100% sure if we're gonna succeed on that, but at least I'm gonna outline the ideas that I would like to use for speeding up the type checking for the compiler. So we'll see how it goes. Maybe those ideas are gonna be wrong. It's all about exploration anyway, right? So twitch.tv/todding, and I'm gonna ping everyone who wants to be pink, and there we go. We officially start the stream. Hello everyone and welcome. So let me go to my compiler development folder and fetch the latest stuff. Right, so let's see. Hello, welcome. How are you guys doing? Merge origin master. So I've done quite a few things off screen, and let me actually git clean everything just in case, right? Just to start fresh and quickly rebootstrap the compiler, right? So there should be something like this. So let's do Wasm, right? Then I'm gonna find the second thing. So I'm gonna make this executable, and then I'm gonna just bootstrap the compiler, right? So and then I can recompile the compiler how many times I want. There we go. So I keep recompiling the compiler. One thing you may notice actually is that the type checking of the whole compiler takes way less time, actually 1 magnitude less time than like the whole compilation. So why would you even want to speed this thing up? It doesn't really show up as some sort of a bottleneck. It's actually super fast. And the reason why I want to speed it up, that in reality, the type checking is actually exponential. Not everybody knows that, but some people actually notice that, right? Some people notice that it's exponential, and in certain circumstances, this causes a problem. And let me actually demonstrate you. So let's actually write a very simple program, right? So I'm going to include something like std port, and let's just introduce an entry point, right? So we have an entry point in here. Right, there we go. So as you can see, the compilation went quite fast, right? So and you can see that the type checking is super fast, right? Again, actually like still 1 magnitude faster than the compilation. All right, let's introduce a very simple thing. Let's introduce an empty if condition, like if true, do nothing, right? So, and let's see how that affects the compilation. Nothing really changed. But what if I add another condition? So let's take a look at the time of the compilation. By the way, can you see everything? I think you should be able to see everything. And I just realized that I forgot to put like a window behind my camera so I know what you can and what you cannot see. Right, this is actually very important, so I can organize things the way, like, if I don't see something, you also can't see something, and I just know that. All right, so if I recompile, it actually jumped up. Right, so it kind of becomes slower. Look. It's climbing up. Now they're basically like on the same magnitude. What if I add another line in here, like so? Nothing pretty much changed. What about another line? Okay, so what if I keep adding them? What if I add this amount of these lines? All right, nothing changing so far. What if I keep adding them? Am I doing the right thing? Because at this point... Okay, so I think it is getting slower, right? So it's like constantly around like, 0.20. It's constantly around 0.20. And this program, by the way, doesn't really do anything, right? So if I keep adding more things, okay, it's around 30 now. Now, if I add more of these things... All right, so it's actually now slower, constantly slower than the compilation. Look at that. And it's actually like, you can perceive that. You can perceive how slow it is. And if you keep adding these things, at some point, it's going to become half of a second. And you can add another one. And at some point, it becomes a second. And let's keep adding more of these things. Now it's 2.5 of a second. What if we add another one? Now it's 5 seconds. You see what I mean? This shit sucks. And okay, so the reason why it is like that. So it only took like 20 conditions to actually get there. So the reason why it works like that is that because the type checker traverses all of the possible control flows. All of them. And here's an interesting thing about if. If is actually forks the control flow, right? It will go inside of the body of the if it is true, and it will go over it if it's false, right? So basically, once you hit if, the type checking splits in half. Then these two split type checking hit another if, which splits them in half, which turns them into 4. Type checking. Now then it goes to 8, 16, 32, 64, 128, and as you can see, like powers of 2, and it grows exponentially. It grows exponentially because it tries to traverse through all of these possible control flows. And in fact, the fact that the compiler can type check itself faster than it compiles itself is nothing of a miracle, actually. Nothing short of a miracle. Is that how we say that in English? I'm not sure. I'm just trying to speak fancy. In fact, like I cannot speak fancy, but I'm trying to. So yeah, it is truly a miracle that I shaped the code in a way that the exponential algorithm of the type checking doesn't get in my way. Right, but it's still there and it still causes some problems. And this is something that I would like to actually try to address on today's stream and see if we can sort of like fix that. I have a couple of ideas on a paper that will work linearly, right? We can get it down to linear time, but that will require a little bit of work. We'll see how it goes. We'll see how it goes. So that's basically the premise of today's stream, and so people already subscribed. Thank you so much, Matthews F777 for 38 months of tier 1 subscription. Thank you. And thank you so much, Lindra Bagger, for 15 months of Twitch Prime subscription. And Lori Master, thank you so much for 27 months of Twitch Prime subscription. Couldn't use Prime for a while because of Amazon strangeness. Happy I can support you again. Thank you so much for the support. And you don't have to, but I really appreciate that anyway. So. Okay, to understand how we can fix this entire thing, we need to understand how we type check in the first place. As already mentioned multiple times, the type checking of the language is inspired by a Wasm Verification step. Right, I don't really know precisely how Wasm Verification step work. Okay, so I think I did a fucky wucky. All right, so you can read about this thing in here. So, and also I'm going to put that in the description. So, web assembly verification. Right, so here is this thing. But the idea that I got from this article, right, is that basically you try to interpret the code, right? So you basically interpret the code as you would normally do. So in here, if you have a simple program, 34 or 35 plus and print, right? You just go and interpret the program, but instead of pushing actual values, you would push types, right? So let me show you. So you encounter 34. And you know that 34 is an integer, right? So you would push integer into the stack, Right, so then you encounter 35. It's basically the process of type checking. And you know 35 is an integer, you push integer onto the stack. So the top of the stack is at the bottom, right? So it grows down in this specific case because it's easier for me to just add elements in there. So then you encounter plus. You know that plus accepts two integers and returns one integer. So you look at the top of the stack. Do I have two integers? Okay, I do have two integers, so I take them out and push a new integer on top of the stack. Then I encounter print. I know that print accepts any element and prints it as an integer, so I check, do I have any element on the stack? Okay, I have some integer, so I print it and I have nothing on the stack. And according to the contract of this procedure, there should be nothing returned from this procedure. I look at the stack. Do I have nothing on the stack? Yes, I do have nothing on the stack, so everything type checked correctly. So as you can see, I didn't have to actually perform the program. What I had to do, I had to sort of like meta execute the program instead of using the types of the things instead of their values. Right, and every time, for instance, if I encounter if, I would split the type checking thread in half. In fact, it's a recursive function. And then I would check what's going to happen if I execute starting from here, the body and everything after the body, and see if it type checks. And then I'll try to execute skipping the body and executing everything after the body. If both of these paths type check, that means the whole thing also type checks. So this is how I deal with the control flow. So that's essentially how it works. So, and also there is a little bit of weirdness with loops, right? Because you have to essentially, because you have sort of infinite process. And for the loops, I basically treat the body of the loop as a separate procedure, right? So maybe we can even put some sort of a condition in here. So while condition do end, and basically everything between while and end right now, I'm not saying that it's going to be like that in the future, and I'm not saying that it's the best way to do that. It is right now. The way it's treated right now is that I basically start type checking this block as a separate procedure, where the expected output of the procedure is the state of the stack before the while. You see what I mean? Right, so basically execute up until this procedure, and we know the state of the stack up until this loop. Then I start a new sort of type checking that type checks the procedure. Even for that procedure, I say, okay, at the end of this procedure, you should have this this sort of stack. And that's it. That's how it works right now. So not perfect, but it's sort of a hack to get around for now. So that's basically the entire type checking, actually. That's basically the entire type checking. So another probably interesting thing would be to know how do I do a backtracking, right? Because I need to basically take snapshots of the states of the stack, right, and go back to a particular time to like keep backtracking all of the possible control flows, and that requires a lot of memory copying and stuff like that. It's like very complicated memory management, so I can also explain how that works as well. So but before, I want to acknowledge everyone who donated and subscribed. Nilete cheered with 100 Bitcoin, saying, have you found a replacement for your tablet? No, I haven't. I'm using my old tablet, which actually not fully broken. It's just like its wire got busted, so it has to be in a very specific place for it to work. I'm gonna keep it like that for a while until I buy a replacement. It's just like there's no problem with buying a replacement. It's just like I have to do that, and sometimes for me it is difficult to do such simple things. Okay, Kavantex, thank you so much for 3 months of tier 1 subscription. Thank you, thank you, thank you. And Mr. Dr. Depression, thank you so much for Twitch Prime subscription, your first subscription, by the way. And welcome to our epic Port Club. All right. So, what do we have? So type checking is just a stack. Well, type checking is basically simulating what's going to be at the runtime, but instead of values, using types. Okay, so how do I make so many copies of different stacks to actually facilitate facilitate the backtracking. This one is actually really interesting because I designed the data structure that I would use for easily copying the stack on the stream, on my last Rust stream. So let me actually go to ToDo Daily, and yeah, so let me quickly find it. I wonder if it's still there. It was about the reference counting, but I'm not 100% sure. It had So if I do Control F for Rust, does it have any? Yeah, there we go. Memory management experiments in Rust. So basically I was experimenting with memory management to actually find a perfect strategy specifically for Porth. All right, so you can actually find it in here, and I'm gonna put it in the description. So there you go. So memory management experiments in Rust, Porth, episode 31. And the data structure I came up with, I basically came up with a tree. I essentially use a tree to keep track of the stacks. However crazy that sounds, but I do use a tree to keep track of the type stacks. And it's actually very fascinating. This is something that I sort of like discovered that you can do. And it makes the memory management hella easier. You won't believe how easy it makes. So I'm gonna actually tell you that for type stacks, I'm using something very sacrilegious, right? I'm using something sacrilegious. I'm using linked lists. Yes, for the type stacks, I use linked lists. Right, so, and this is how it works. If I need to push, hopefully my tablet is not gonna die today. So if I need to push an element on the type stack, I just create a node in a linked list. Then I wanna push another element on the data stack. I create a new node, and the top of the data stack refers to the previous node. So the top is here, right? The top of the type stack is here, and the next element is here, and this thing then points at like empty list and nothing, right? And this is how a single type stack looks like. If at any point I want to make a copy, right? I want to make a copy of this type stack. What I'm doing, in fact, I'm just creating a second pointer to that specific top of the stack. And then I push a new element on that new stack, and it just looks like this, right? And then I want to push another element to this stack, and it's gonna look like this. And these things are gonna be new tops of the two separate stacks. So as you can see, it's a persistent data structure that actually stores all of the previous states of itself, but also adds sort of like the diff on the next state. And what you end up with at the end of the day is this huge tree, right? Huge tree of different sort of stacks, of different states of the stacks, and so on and so forth, and which are super easy to copy. Right. And if you want to remove an element, let's actually imagine that this is top of your stack, and that means your stack is something like this, right? So your stack looks like something like this. You can always traverse to the bottom of the stack just by following this reference until you reach the end. So if you want to remove the element, you just move your pointer here. But this thing still stays in here because just in case maybe there is another stack that is pointing in here, right? So all of the possible copies of the stack, they stay intact. It's just like the tree that grows. So this is basically how we maintain different type stacks, if that makes any sense. So Pakel1, I hope I pronounced your nickname correctly. Thank you so much for 7 months of Twitch Prime subscription. Thank you, thank you, thank you. And Mac5A, I hope I pronounced the nickname correctly as well. Thank you so much for Twitch Prime, your first subscription, by the way, and welcome to our epic portal. So as you can see, the type stacks are very lightweight. They are extremely lightweight. And you know, they're lightweight for the same reason why branches in Git are lightweight. Doesn't that remind you of something? doesn't look like a Git history? That is basically a Git history, actually. And in Git, branching is very lightweight because of that, right? Because it's super easy to just create like pointers. And because of that, the type stacks in Porth, like in the Porth type checker, also very lightweight, and you can actually copy them super easily and super fast. So that is very cool. So what is the idea that I have to speed up the type checking dramatically? Imagine that I have a simple program. Let's actually write a simple program. 34, 35, right? So I'm gonna write it like that. So each individual operation is on a separate line, right? So then we have plus, then we have 69, then equals if. I'm gonna print hello. I'm gonna print nice, right? I'm gonna put puts, and then we're gonna put and then I'm gonna say okay. I'm gonna put in here. There we go. So how can we perform the type checking? We're going to interpret the program as usual by pushing the types of the elements we encounter, by changing the stack accordingly and stuff like that. But we're gonna have a separate data structure. We're gonna have a separate data structure where for each operation, we also store the snapshot of the stack, the whole snapshot. Since the type stacks are so lightweight, taking a snapshot of the whole stack is cheap, right? Because it's just a pointer at the top of the stack. So you would have a snapshot in here, right? So this is going to be S1, then S2. We literally like saving the whole stack on each individual operation. So this one is going to be something like this. So S4, then S5. Then we encounter if, right? We encounter if. And let's split our type checking in two and first go over if. Right, we went over if, and now we have the state S6, and then we have a state S7, and then at the end of this sort of branch where we jumped over if, we realized that we didn't have nothing on the stack, so everything's fine. Okay, now we go into the branch inside of if. As you can see, we sort of marked each individual operation as type checked. Right, we visited these things, and the only things that are not visited are these things. Right, so this one, I can probably say as 6, maybe 7 and 8. Okay, so then I do the following things. So this is going to be S7 prime, because it's slightly different S7. Then I do S8, and then I go to the next operation and realized, oh, I already visited it. And what I'm going to do, I'm going to take my current state of the stack and check, is that the same state as this one? If it is, I know that the rest of the stuff is going to be type checked perfectly. If not, this is where I can report an error. That way, I actually went over each individual instruction only once, because I marked what I already visited. And if I already visited something, I don't visit that again. I just check if the state that I reached at that point is the same as the state when I reached from a different path. So that reduces the complexity from the exponential one to a linear one. So yeah. And by the way, do feel free to steal that idea for your programming language. I would be super happy if you do that. For your programming language, do steal that idea. And this is only on the paper, right? First of all, this is only on the paper, and I don't know how it's gonna work out when we'll try to put that in practice, right? So if it works out, I'm gonna be poked out of my mind, actually. So it would be actually super cool. So essentially, we're using a Git approach to type check in the stack-based language. Did I steal it from somewhere else already? I didn't really steal it from somewhere else. I sort of logically came up with this approach and then realized that Git uses the same approach. So I can say that I steal it from Linus, but I don't know, like, so. I mean, this is a persistent data structure, and people were using persistent data structure to compress the complexity of algorithm for ages, right? It's not like I invented something super new, right? And to be fair, I need to read that article on the Wasm verification, because maybe like Wasm also uses something like that, right? So yeah. Like the only thing I got from this article, I just briefly looked through this article, got the idea of like evaluating the program like with types instead of values, and got hooked into that idea and tried to like evolve from that idea. But I didn't go into the details how they manage the control flow and stuff like that. So they actually have like very specific things for control flow. So yeah. Okay, so this was basically the idea. Thank you so much, Ka-Chu, for tier 1 subscription. Your first subscription, by the way. Welcome to our epic Port Club. And Sgualda9, I hope I pronounced the nickname correctly. Thank you so much for 2 months of Twitch Prime subscription. Absolutely fucking epic. Thank you, thank you, thank you. So. I wrote a compiler with a team using a camel and was in charge of type checking. It can get complicated. Yeah, I know. Porst is not the first language that I wrote, not the first statically typed checked language. It is very complicated. Type checking is in fact very complicated topic. That's gonna be a nice clickbait vote on YouTube. Oh, you mean mentioning Git? Okay, thank you so much for the clickbait idea. So yeah. I stole idea from Linus Torvalds. Oh, that isn't that epic? Holy fucking shit! No. You know what it is? You know what this is? This is not Git. This is a blockchain. I'm type checking with crypto and NFTs. Holy fucking shit! Anyway, I'm joking. I don't know. We'll see. So let's take a look. Ganovi Banana, thank you so much for a 19 month of tier 1 subscription. Thank you. And Dorn, thank you so much for tier 1 subscription. Your first subscription, by the way. Welcome to Epic Port Club. NFT language confirmed. Yeah, exactly. Okay, so let's take a look. So we have the definition of the type stack somewhere here, size of type stack. So first of all, we have a type frame. This is a simple structure that holds a type, the location where that type was introduced, right? Location in the source code. Location is basically 3 things: the line, the column, and the file name. So it's used in diagnostics, right? So it basically the way the compiler can tell you where exactly the error has happened and stuff like that. And the previous frame, right? So you can just follow this pointer and reach to the next frame. So on top of that, we have a type stack, and type stack only holds of the top of the stack, plus it also keeps tracks of the count, just in case you need to know how many elements are on the stack and you don't want to actually follow the full chain. It's kind of a weird optimization. I don't really know why I introduced it. It's not because I introduced it because it was slow. It wasn't slow. The stacks don't really grow very, very high. They're usually like maybe 20 elements max. I didn't really have to do that. I think the only reason I introduced this count is because at the time, language didn't even have any bindings, like let bindings, and programming in that language was even more difficult than it is right now. So to minimize the amount of like code that I have to write in this painful language, I just like, you know, cache that information so I can just grab it out of the structure directly. In fact, like with let bindings, like a lot of code, a lot of tricks that I came up with are not really needed. Right now the writing code is a little bit easier. Not as easy as I would want to, right? Because I would like to have a better type system, right? With more rich types, right? For example, with properly typed pointers, for instance. Right now, pointers, all of the pointers in this language act like void star in C, which is annoying, right? because if I change the signature of the procedure, I cannot follow the compilation errors and stuff like that. It's like, yeah, it is what it is. But yeah, anyway, so this count is not particularly needed. So this is the definition of the type stack. And on top of that, we also have so-called type frame pool. Type frame pool. It's a global array of pre-allocated type frames. We have 16,000 of pre-allocated type frames, right? Every time you push a new frame onto the stack, it just allocates a new frame in that pool, right? It gives you the new frame in that pool. And then you just use these frames in the stacks, right? So the entire tree in here is actually stored in a linear array, and the elements of the array cross-refer to each other. So yeah. Though, unfortunately, they cross-refer to each other using absolute pointers, which makes this array not growable. But in the future, I'm going to rewrite it so they refer to each other using indices within that array, which will make this entire array growable in dynamic memory when we implement like dynamic memory, like allocation and stuff like that. So, but for now, we just pre-allocate big enough array and just be happy with it, I suppose. Much like NFTs, we're already pogging out of our minds at vague designs with no implementation yet. You're right. Thank you so much. Okay, so so it's like a polite reminder that let's just start writing code already. Okay. Let me see. I'm going to go into the type checking code, and this is where we type check things, right? So there's a function expect arity, which accepts the type stack and the arity, how many elements you expect on that stack. And yeah, so if there's not enough elements, it issues the diagnostic. If there is enough elements, it returns those elements separated from the stack. So snap back to reality. Snap back to reality, expect arity. So, and yeah, somewhere here we'll have to pre-allocate an array for the snapshots of the context and stuff like that. So let me see. Oh boy. So I think I need to take a look at the compiler. So there is an ops array. So where's the ops array? Here's the ops array, and we have 64,000 operations, right? We have 64,000 operations. The print intrinsics is straight up stolen from, I think, either GCC or client. Yeah, it is stolen from GCC, but I think we can already remove it. Right, the only reason I kept it is because it would allow me to print things without including the whole standard library, which would pollute the assembly. But now we introduced dead code elimination, and it doesn't matter anymore, right? Because I can just include the standard library and print number, and it's not going to generate too much code, because all of the unused code is going to be removed. So I can actually even show you. So I think I already showed that, but I can show that again. So I'm going to compile the hello world from examples. We have hello world from examples. And there you go. And if I take a look at the examples, hello world assembly, that's the whole assembly, right? So that's the whole program. Yeah. So that's the whole hello world program generated from, from port. So the compiler removed the whole standard library, and also it removed all of the strings from the standard library. So the only string that is left in here is the hello world string. So maybe at this point we can just remove the print, right? Because we have things like put u and put I, and it's just like, yeah, we can just use those. So yeah, we do have that string elimination. We don't have a that global memories elimination. So if there are any global memories within the standard library, they're going to be appended to the global memory section here. So your program is going to allocate more memory than it actually needs. But I was too lazy to actually get rid of that. So yeah, I don't know. So here's the global memory, here's the return stack, and I think maybe at some point I'm going to actually merge them together. So I'm going to know the offset of the return stack, right? So there's no need to to actually have these labels, human readable labels. All right, so let me see. So what I was doing. Okay, so I also should keep track not only of the of the data stack, right, for each individual operation, but also keep track of the return stack, right, because return stack is also part of the state. So it is in fact quite important. I think. Is it? Is it quite important? That's a good question, actually. Maybe it doesn't. There is some property of the return stack that is not that important. So yeah, we'll see. So I'm gonna keep track only of the data stack, because I think I can feel that there is some property of the LED bindings that kind of hold and allow you to not keep track of the return stack, because there's also like matching unbind and stuff like that, so it should be fine. Okay, so where's the check? And let's introduce a structure, right? Let's introduce some sort of a structure, and the structure is going to be, let's call it snapshot, I suppose. Size of snapshot. It's going to be a reset. Let's call it maybe type snap, right? Type snap. Snap back to reality. Expect RT. Type snap. So what we're gonna have in here, I suppose maybe we're gonna just have the stack, right? So this is gonna be the stack, and the size of this entire thing is gonna be size of the type stack. Offset, and there we go. So this is a type snaps, and let's introduce literally type snaps. Oh, by the way, I think we also need some sort of a boolean that indicates that we already visited that specific place, right? So we'll need something like type snap visited, and it's going to be size of boolean, offset, and let's actually align offset. There we go. Looks like shit. I don't even know. Whatever. Bike shading alignment. And let's allocate the array of type snaps, right? So it's going to be something like memory type snaps, and we're going to take size of type snap and multiply it by the ops capacity, right? Because for each operation in the ops array, we have the snapshot for this specific thing, right? So it's going to be something like that. The question is, what's going to be the size of this entire thing? I feel like the size is going to be pretty big, right? Because we have 64,000 operations, and plus the size of this entire thing, even though by itself it's pretty small, it can get relatively big. So let me go to the main entry, right? So here's the main entry, and let's just print the value of this entire thing, right? So what's going to be the value? It's going to be like this. Snap back to reality. Expect. I'm sorry. Can't help myself. So let me see. So I'm gonna take the Bootstrap compiler, and I'm just gonna run this entire thing. And what's the size of this entire stuff? Okay, so we have this amount of kilobytes, and we have 1.5 megabytes. Can I afford 1.5 megabytes in 2022 for the entire thing? I think I should be able to afford that, right? I'm pretty sure. Jan18383, thank you so much for 4 months of Twitch Prime subscription. Thank you. Zozi Best Ozzy. It's like Ozzy Osbourne, right? I don't know. Thank you so much for 4 months of Twitch Prime. Programming in PHP is actually quite hard. Especially with the type system of PHP constantly trying to screw you over. So you have to have a lot of experience in PHP to be super productive in PHP. So, so there's one example in PHP that I constantly bring up. PHP MD5 conversion. Right. So, anyway, I forgot. Convert MD5. Something like compare, and it was on Stack Overflow. Does anyone remember the link? Compare to MD, yeah. I think that was the thing, no? God damn it. I don't remember. So the thing was, somebody was trying to compare two like strings, like hash strings, MD5 hash strings, and because they both looked like a floating point number, PHP convert them both to floating point numbers and compare them as floating point numbers, right? So and you use just double equals, not triple equals, right? But I mean, it's insane, right? It's insane even for such a dynamic language, right? You have two strings which are explicitly said to be two strings, and you compare two strings, and when you try to compare two strings, they're compared like numbers. I mean, I understand that equals equals is pretty crazy thing and you should not use that, but that is too crazy even for just double equals. It's just like, even for JavaScript doesn't try to screw you over this much. It's just... Does anyone know what I'm talking about? This is just like insane. And you have to have like a lot of experience with this language to be productive in it and not fall into these traps all the time. Right, so, and it's just like people who work professionally as PHP developers and write big stuff in PHP, I have a huge respect for, because like, holy fuck. I don't know. All right, thank you so much, Hookson69 for Twitch Prime subscription. Thank you. Welcome to our Epic Port Club. All right, so let me see. So this size is not that big, so it should be fine, right? It should be fine. So let me go to check, and we already pre-allocated the memory. And if I try to basically recompile the compiler, right? I'm recompiling the compiler, right? And if I take a look at the compiler assembly in here, so the full size of the memory is around like this. So this is how many kilobytes. So the compiler itself like requires 17 megabytes of memory, right? So which is fine, I guess, right? So we are not consuming that much. But maybe in the future we're going to be using some sort of a hash map for this entire thing. Some sort of a hash map. Okay. So now, what I want to do, every time we type check something, so there's a procedure called type check program from, right? So essentially it accepts the type context, right? So this is a type context. So, and the type context is a structure that contains the stack, the current IP that we're checking, what are the expected outputs. Also, there is a thing, block start IP. This is where the procedure starts, right? So IP is the current checking, but this is where the procedure has started. Or loop, actually, because we're treating type checking of loops as checking procedures, so whatever. And we also have a return stack in here. So this is the context, right? So this is essentially the context. And we're starting to type check from this specific place. So what I'm thinking is that I'm gonna start, okay, I am currently on IP, right? I am currently on IP. So after this entire thing, I'm going to finish handling like one single operation. So I need to find the other end. So how many spaces do I have in here? I have 6 spaces. So let me quickly find the other end. So this is basically a huge switch case on different operations and different intrinsics, right? So that's what we have in here. And this is 8 characters, and this is essentially 6 characters. So this is where I think I would take the current context. I will take the current context and save it into this snapshot, right? So this is, I think, where I would do. So I'm going to mark it as to do in here, and I'm going to go back to proc. Right, so this is roughly where it is, right? So this is IP, and there's also this stack. I can do ToDo. And okay, so that means I can do type snaps, right? I can do type snaps. And I'm going to take IP and multiply it by the size of the type snap. right? So this is basically how I access the elements of the array, right? So this is how I access the elements of the array. So this is a type snap. I multiplied, that creates an offset, and I have set this pointer by that specific offset, and I got the pointer to the type snap at the of this thing, right? Okay, might as well actually start something like this. I think it has to be something like this. So this is IP, I multiply it, offset it, then type snap. I suppose I can take visited. Might as well, by the way, just do something like this and bind it to like this thing, right? So now I just have a pointer to like this specific type snap that I can work with. And for instance, I can say that this specific snap was visited, right? So it's going to be visited, and I'm going to save it as a boolean. There we go. I marked it as visited. Cool. So, and then I also want to copy the current state of the stack into the type snap. By the way, did I call type snap a stack? Right, I did call it stack. So I'm going to take the stack, right, and I think I have a mem copy somewhere, right? So I have a mem copy somewhere. I think it is in the std port, right? Mem copy. So we take the size of type stack. Then the source is the stack I'm copying, right? So this is the stack, and the destination is the thing that we have in a snap. Snap, type snap, stack pointer plus, and I do mem copy. Mem copy returns the pointer to the destination. We can drop that entire thing. So every time we type check a specific IP, every time we type check the specific IP, we just making a snapshot, right? We're just making a snapshot. We're just making a snapshot. So yes. Okay, just checking this thing, and I need to think about the next step. Okay, it will just save all of these things, right? It will just save all of these things, but it's not gonna use any of that information anywhere, right? So one of the things we can try to do, maybe if we sort of visited this thing again, just do something about that thing, you know? Just do something about it. But how can we do something about it? Right, so we might go to the beginning of the procedure, right? To the beginning of the procedure like so. Right, so type check program from. So here, right, we found out the current IP, right? What we can do, right, with that IP, we can take the current snap of that thing, right? We take the current snap and check if it was already visited. And if it's not visited, only then we're gonna do this entire thing. If it was visited, that means we're gonna take the current state, we're gonna take the current state, and we're gonna take the snap state, and we're just gonna compare them together, right? We're gonna compare them together. And as far as I know, we even have an operation for that. Right, so proc type check stack, I think. Maybe, I don't quite remember, right? So this thing essentially, oh yeah, well, yeah, this one doesn't really do what I think it does, right? It does a slightly different thing. So we just need to make sure that these two things are the same thing. I'd love a language that doesn't use pointers. There's plenty of such languages. In fact, I think majority of the languages don't use pointers, so why create another one? Why did you remove the source code from the repo? I didn't remove the source code from the repo. The source code is still there. So all of the 1,188 commits that are published under MIT license are still there, and they're still under MIT license, and you can do whatever you want with them under MIT license. The way you can access them is basically cloning this repo and doing git checkout. Follow these instructions in here. Everything that was published is still open, and you can do whatever you want with it. What I'm basically doing, I'm not pushing any new code under MIT. So that's basically it. Everything that is pushed under MIT is still under MIT, and it is open. You can do whatever you want with it. I'm just not pushing any new MIT code until I'm done with the design. Does that make any sense? I did not close the source code. The source code is open. Here it is. 1,188 commits are still intact. They're still yours. What's the new license? The new license, well, there is no new license. There's only one license, MIT. It's just like the new code that I create is simply not published. So, yeah, that's it. It doesn't have a license. It's just, it's not published. Why all of the drama about court? I have no idea what is court, I'm sorry. I'm hearing that thing for the first time. Do you still program in Haskell? Occasionally, not always. All right, so let's continue. AOC in ports this year, and I'm kind of over AOC, I'm sorry. I do not enjoy it. The last time I participated in AOC, I actually regretted it because I looked back and I realized that I didn't work on ports for the whole month. So I didn't enjoy it per se. It was just like a bunch of annoying challenges, and I just, at the end of this entire thing, I didn't even finish it. I just wanted my time back so I could work on port. So I'm not participating in AOC anymore, I'm sorry. It's definitely not for me. I have way too much stuff to work on. Way too much stuff. All right. Let me see. So maybe I want to make a small break because I want to refill my cup of tea. So let's quickly refill a cup of tea, and well, let's continue working on this entire thing. So it's kind of like chicken and egg problem, right? I'm not really sure how like start on this entire thing, but let me see. Type check program from. Right, so this is basically all of these things, right? Type check for a program from. This is the IP, and maybe I want to kind of move, like figuring out the snap at the top, right? So let's actually go back, and here is IP. So I might as well just do something like over, right? So I know that here in this, on the stack I have like the pointer to the stack, to the type stack, and then the IP. I can sort of copy this thing over and then get the snap, so I have the snap somewhere here, right? So, and then at the bottom here, I won't need any of this stuff, right? I just won't need any of this stuff, like this. As you can see, snap is defined at the beginning of this huge loop, right? So this is a huge loop that just iterates over like everything, and yeah, basically type checks everything. All right, so let me see if this entire thing still compiles, right? It seems to be, okay, so it doesn't really work that well. Okay, so because pointer in here, oh, this one is annoying. All right. So because it may accidentally jump, yeah, it may jump to a completely different place. So what I have to do in here, in fact, I have to read from the pointer to IP, only then it will kind of work. Yeah, I see. Yeah, and if I try to recompile this thing with itself, I might as well actually do two-stage compilation, right? It's going to be two-stage compilation, right? And it seems to be, you know, recompiling itself, which is nice. All right, so, and this is where I can essentially check, right, the state of the snap, right? So the state of the snap. Right. So snap, type snap visited, pointer plus, and I read it as a boolean, right? So I need to read it as a boolean. If it was visited, right? If it was visited, there's nothing much to check anymore, right? So the only thing we need to do essentially is just, you know, let's put it this way, right? Take the snap type snap stack, pointer plus, so we have this stack and the current stack, and compare their contents, right? So if they have the same contents, that means everything's fine and we don't have to continue. If they have a different one, we have to report an error. If we never visited this specific like place, that means we need to do whatever we have there at the bottom, and then also need to mark the snap as visited and also snapshot the stack. So that's basically the idea, right? So here maybe I'm going to do it like this, right? If it's not, right? If it's not visited, we have to do the rest of the stuff in here, right? So let me try to find ToDo. So here is the ToDo, and I want to like offset it like so, right? So, and in here, we have the situation when it's not implemented yet, right? So type checking already visited type snaps is not implemented yet. There we go. So, and in here we have another thing that is, yeah, we just have to like mark everything. So it's going to be true, snap type snap visited pointer plus, and I just save it as visited. Then, so I removed that code, so I'm basically replicating that code again. Okay. So because I thought that maybe I will not need it there, but yeah, sometimes it is like that. Size of type stack, the source is the stack, then the destination is a snap, type snap stack pointer plus, and then I do mem copy, and then I just drop this entire thing because I don't really need the destination of this entire thing. All right, so this is a size, snap, and I think that is basically it. And let me go at the top in here, right? Okay, that's very, very cool. That is very, very cool. We just type check this entire thing, and that is basically it. TMP rewind. So this one is weird. I probably know why. Because here, yeah, we're supposed to return the true, right? So touch check already visited. So I suppose here we'll have to return false, right? Break, because we reached already visited code, right? So we already reached the visited code, and hopefully this thing is gonna just compile, and there we go. So we hit a pretty interesting spot. Type checking already visited type snaps is not implemented, right? So that means we've got the situation of trying to visit something that we already visited before. We just don't know how to type check and report errors in that particular case. So everything seems to be working as like expected, more or less. So that's actually super cool. Super cool. So we can try to do something interesting in here. We can try to print the location, right? The current sort of location. How can we even do that? So we know the IP, right? We know the IP. I can take the IP, like so, then I can multiply by the size of the ops, size of the op, I multiply it by that, then I take the ops and I offset by this entire thing, so then I can take the token associated with that operation, and then within the token I can get the location in the source code, and I can say located here, which will print the diagnostic that tells the user where exactly this operation is located. So, and this is how we're gonna know what operation we visited the second time. Yeah, Kolumbetka, yeah, it is dang, it is super dang. So we have an index, we transform an index into the offset, into the pointer offset. We use that pointer offset to get the pointer to the element, then we offset to the field of token, and within the structure token we offset to the field location, and we pass the pointer to the location to the located here, which prints the diagnostic. Right, so, and it's kind of equivalent of, like, if you have ops, you just take IP, then token, location. Right, so this is kind of equivalent to this in C. Right, but because we're programming in a shady language that we try to make less shady, we have to write like that for now. Will we draw dot graphs today? I'm not sure, we'll see, we'll see. So, okay, so let's go. Okay, so it's already happened in the standard library, so I'm going to predict that it has something to do with if condition. There we go. Right, so we tried to visit this thing twice, right, which is rather interesting. Because, okay, so we started to go here, so if basically went to here and then jumped here and then, okay, so I can see that because both of the branches of if jump at the end to the end, right? So we kind of visited this end 2 times, right? So we visited it 2 times. All right, that's pretty cool. That is in fact pretty cool. And how can we type check this entire thing? So the way we can type check this entire thing is just like, yeah, we have the stack and we have this snapshot, right? Can we just compare them together, right? So as I already said, we have a special function for that. Type check stack. So it accepts the token. I think it's for the operation we're doing. I think it is for the operation we're doing. Right. Then we take the stack, we see, so I don't think this operation is actually acceptable, because what we have in here is we have stack and what we expect on the top of the stack, right? What we expect on the top of the stack, and then what we accept on the top of the stack after we apply this operation. Right, so this is more of a like for type checking plus, right? Because as you know, plus. Can I see anything? Plus, right? So as input, it accepts 2 integers, and as output, it returns 1 integer. So if you have a stack that looks like pointer, integer. What's up with Emacs? This thing should just work, right? So it will take this stack, it will take ints, and we'll check, okay, so do we have 2 integers on the top? Yes, we do have. We're gonna take them out, and then since outs is a single integer, we're gonna replace them with int. So this is basically what this entire function does, and I don't think it is applicable in here. I don't think it is applicable. So what we need to do something that we do at the end of the procedure checking, right? So at the end of each procedure, we sort of like have an output of the procedure, and we just check if it's equal to the output. So how do we even do that? I think we do it something like this. All right. So type check program. Cool. So we take the current stack. And we take the what is expected output, right? So we do that. Then we check the okay, so if we check if we have insufficient amount of elements or sufficient amount of elements, right? So if we have insufficient amount of elements, we report one thing, otherwise we report the other thing. And after that, I suppose well, I don't see where we iterate over the stacks and compare the frames. I don't see this thing here for some reason. Right, so let me see. So here's when one thing is bigger. Right, here's the thing when one thing is that. If they're equal, do we even compare them? This is really weird. Why don't we compare them to anything? There should be some sort of a check. Because if if I understand correctly what I see, something like proc foo pointer in, right, 4242 should just work, because I don't see where we check the specific types of the output stack. So this is kind of weird. Do we have a bug that's been sneaking around for ages? So this is a very interesting question. So let me take a look. No, we don't. Okay, so unexpected data on the stack at the end of the procedure, expected elements. Okay, so let's actually find this diagnostic, right? So the easiest way to navigate in the code is just to search for the diagnostics. Oh yeah, okay, here it is. Oh, I see. Oh, I see. Okay, so the code that actually checks this entire stuff was here. Okay, so this is the loop, right? So we have a stack and expected outputs, right? Stack and expected outputs, and we pop from both of the stack. What the fuck am I doing? And then if some of the frames don't match up, we report the error essentially, right? So we report the error. So this before this snapshot approach, this was only happening at the end of the procedures. I think this is going to happen now every time we check something that we already visited before. So I think it makes sense to extract this entire thing into a separate procedure that we can reuse. I think that's what's needed to be done in here, right? So let's do proc, and it's going to be type check expected outs, right? So maybe we're gonna call it type check outs. No, let's call it type check expected. Right, so I don't really know what we're gonna accept in this entire thing, but I'm gonna figure it out by copy pasting like literally everything, right? By copy pasting literally everything. And also the code that reports sufficient, insufficient stuff, all of that is gonna be copy pasted as well, right? All of that is going to be copy-pasted as well. That's a lot of code actually, right? And this code is written in old Porth style before we had any lead binding. So we're going to have a good time sort of like cleaning up this entire thing, if you know what I mean. Right, so this is going to be something like this. All right, there we go. Hopefully, so that's kind of it. All right, so as you can see here, the main two things that we have is the stack itself, right? So here is the stack and the outs, right? And we're gonna basically bind both of these things. So this is the stack, this is outs, So let me find an end, and this is where we clean everything up. Right, and here's the interesting part. So I do over, this is another over, and I feel like I forgot to maybe drop this entire thing at the end, right? Because there was some sort of a drop there. I think I forgot that one. Yeah, so this is what I forgot. Okay. This is what I forgot. Cool. So that's a lot of stuff, but that should be okay. And So if I understood everything correctly, I can just do stack outs. I'm gonna push them like this. And interestingly enough, maybe here I'm gonna just do pick stack outs in stack type stack empty outs type stack empty. Either that one or that one are empty. Right, either that one or that one are empty and not. And we're gonna just continue doing this entire thing like this. Okay, so after that, we'll have to bind them within. So I'm starting to feel that maybe the top level bindings in here is not needed. I don't think it's gonna be needed because we're gonna just like thread it through, but I'm gonna keep it here for now. I'm gonna keep it here for now, just in case, but later we'll be able to get rid of it, I think. So there we go. So I'm just organizing the loop. So this is a stack, and this is outs. So this is a stack. This one is weird. Yeah, so it has to be stack. I take the top of the stack, I have set it, I read it, I take the type on top of the stack. So then I take the outs. This one is also weird. So outs. Not quite sure why. Okay, so I take both of these things, and if they are not equal, this is where I start doing things. Right, so this is where I start to distinguish between different kinds of the beginning of the block, right? If you have insufficient data or incompatible data when you're type checking while, or when you type checking procedure or something else. Right, so this is not needed, I think. I don't think it is in fact needed. Right. I'm kind of confused. What are you doing now? I'm developing a programming language. That's what I'm doing right now. Do you write all the code by heart? What is that supposed to mean? I know what I want to achieve. I analyze the current situation, and I come up with the solution how to move from the current situation to where I want the code to be. So that's basically 3 steps. I figure out what is the point A. I then formalize the point B, and I try to find the path from point A to point B. So that's how I do write code, essentially. Okay. Basically work like a ballistic missile. Exactly, right? So that's basically programming. Programming is just like, imagine that you're a ballistic missile and you're trying to move from point A to point B. So yeah. It is what it is, and it isn't what it isn't. Is it not? I think it is. The missile knows where it is because it knows where it is. So anyway. But I don't really know what you mean by like coding by heart. Probably because I don't really speak English well, so I don't really exactly know what you mean by that. Is that what you mean by heart? Or I don't know. The missile knows its location by subtracting where it isn't from where it is. Exactly, that's how it works. You don't randomly see things you'd like to change and made sporadically changes that struggle to put it in a commit? You know, my problem is that I do. My brain doesn't allow me not to see things that it needs to do. That's my curse. Alright, so that's cool. I need to find... So there was some confusion here, which I don't fully understand. Okay. So I need to find... So there was a plus. Okay. Alright, seems alright. I didn't think there's... Yeah, I think I just accidentally copy-pasted something. There was something weird that just like freaked me out a little bit, but I think everything's fine. I didn't see anything super weird now. Okay, so we have this block that determines like where we are, and I don't think it's that important. So what I need to do here is now basically report Basically report. But where are we right now? Where are we located right now? So we have a block IP, right? So there is that. So I take the token and I just report unexpected in a stack after a single. Yeah, I see. But I want to actually know the current place, right? Where are we currently? That's what I want to know. And maybe this is something that I can actually pass in here, because who said I cannot? So let's actually pass IP in here. Why not? So we know the IP. Cool. And now I can do something like IP multiplied by size of OP, right? Then the same situation. So ops pointer plus, and we've got the IP, right? Might as well actually do that right away. So since this is that, we can pass it as the first thing. So that means in here I can just do it like that. Right, I'm gonna multiply it right away, turning it into ops, and I've got the op. See? So this is gonna be that, and then I can just like use this thing. Right. So I'm going to take OP token, pointer plus, token location, pointer plus, put lock. And in here we're going to say an error. Unexpected data in the stack after a single... okay, unexpected data on this stack. That's what we have. Unexpected data on this stack. And I suppose I'm going to just like put a new line in here. Nothing particularly special. Right, so we're gonna have that, and I should be able to nuke this entire piece of code. Okay, so then I take the top of the stack, right? So then I take the top of the stack yet again, which probably means that I might want to bind these things again so I don't waste any like sort of time, but we'll see. Right, so because we have things like this, right? So there's two tops. Step top. Let me say it. Let's just translate it as it is right now. Right. So let's just translate it as it is. So this is the first top. And in here I just take a location, expected type here, and then I drop that location. And here I just have outs. Right. I just have outs. And I just take the top out of that. And that is basically it. So this is me basically reporting this entire stuff. After that, I just pop the elements out of that stack, out of that thing. Out of that stack, out of that thing. But I actually modify the state. But is that something that I want? Is that something that I actually want? Do I want to modify the state? I don't think so, and I'm not sure if I care. Right, because it's actually kind of a final thing that I do. It is kind of a final thing. So I don't think it matters that much. All right, so let me see. Okay, so here then I just take at the stacks. Maybe it should work fine because it's a pointer to the stack. So yeah, I'm not working on the specific frames, so it should work fine. It should work as expected. Okay, I just got a little bit, worried that maybe I do not fully understand what the hell is going on, but that should be fine. Alright, so this is that. And do I really need to push any of that? I think I do. And that actually, since I'm sort of like referring to them by a reference, I don't think I need any of this stuff. Yeah, okay, because it's like a mutable thing. Okay, so that's cool. So I'm slowly iterating on the refactoring of this specific piece of code. I'm slowly iterating, and it becomes smaller and smaller and more understandable, which I'm super happy about. So, and in here again, so we have two sort of tops, which I would like to maybe somehow bind to something, but I just like, okay, I'm gonna work on that a little bit later. In any case, so this one is gonna be just a stack, right? So this is just a stack. I take the count of this thing, and this is gonna be just outs, and I take the count of these outs, and I just compare them together, right? I just compare them together, and this is a similar thing. This is a similar thing where just depending on the beginning, I report different things. And handle data on this stack. Right. So, and I suppose I will get rid of this entire thing. I'll get rid of this entire thing. So we have OP, so that means I should be able to just use that. It's kind of similar in here too. It's kind of similar in here too. Right. So this is OP. And then this is unhandled data on this stack. Right, so that's the error that we have in here. That's the error. Unhandled data on the stack. And then we print that unhandled data on the stack. That's what we have in here. Yeah. Okay. So cool. This is basically the size of one thing, this is the size of another, so we take OP, this is where it was located and held it on the stack, and we also dump the current state of the stack, and we just exit in here. All right. So, and this like type snap approach also makes the code simpler. As you can see, I'm actually removing the code, which makes it basically simpler. Right, so in here we have a different situation. It's insufficient data, right? I might as well, does it print anything after insufficient data? I think it does, but it prints outs. Okay, so there is a very interesting symmetry in here. And when you have unhandled data, you print the stack itself, right? So you just print the stack. When you have insufficient data, you print expected things. Right, so here's the stack, and you print it here. So might as well just copy paste this entire thing. Then, since we notice this symmetry, we can just do that. Insufficient, right? Insufficient. And this one is just going to be outs. And then that means we can just remove the entire thing in here. All right, we remove the entire thing. And that is basically the whole code that is going to take the current state of the type checking, right, current state of the type checking, the snapshot from previous visiting, and compare them together. That's the whole code, right? We have two stacks, like the current stack, what is expected, and the current operation and stuff like that, and that's what we're doing here. So the code becomes more simpler and simpler, simpler and simpler. So here we have like n and m. I can actually do something like this, right? So let n and m, and these two drops are going to be removed. So this one is n and m, and another over is n and m, right? So this is like basically the sizes of these two stacks. So that's what they are. So does the code become more readable as I remove all of that, you know, crappy stuff from previous versions? I think it becomes more and more readable. I do want to believe so, at least. Okay. So this is the top frames that we have. And we might as well just do something like let stack top and out stop, right? And we can bind these two things and just work on the level of those things, right? So, and in here I can just do something like that. Hopefully that will make the code even more readable. We'll see, we'll see. So this one is a stack top. We take the type, and this one is the out stop, right? So this is the out stop, and these are two frames. Okay, so then I do that, and as you can see here, I'm referring to the stack top yet again. So this is the location, which also means that maybe I can rewrite this entire thing like that. So this is the stack top type frame location, and then this one is stack top type frame type, right? So and let's align input like that. So that became simpler, right? So and now we have outs. This one is gonna be out stop, and we can now also remove this tag and align inputs like that. Interestingly, might as well just, yeah, I can select this entire thing and realign like that, so it looks even better. So whatever we call stack is in fact expected, right? It's a thing that is expected, I mean actual thing. And outs is expected. All right, so can I just reorganize this and call this unexpected? Or maybe actual. Right, so this is going to be called actual, and this one is going to be called expected. Right, so there's actual and there is expected. Right. Actual and expected. So, and this is actual stack and expected stack, which we can also rename like that. Being able to watch hours and hours of ToDo creating language really helps coping with COVID. Oh, you get well soon. Yeah, COVID is a serious thing. Alrighty. Okay, that's pretty cool. So here we also have that and that and that, and I think I'm kind of done rat-holing over this entire procedure. Hopefully, not 100% sure, but I want to get that procedure right, because it's going to be a very crucial procedure in the entire type checking, because again, it takes the current state and it takes expected state and it compares them together. So this is a very crucial procedure, and if we get it right, so we're going to basically win. Coding and import looks so much better with LED bindings. Yes. Thank you so much. All right, so let me take a look. So we have some stuff, and yeah, okay, so I'm not compiling the Porth compiler. Let me try to compile the Porth compiler, and it is compiling apparently. That is very interesting. So it is compiling. Okay, so and I wonder what we can do in here. All right, so when do we reach the end? So I suppose we reach the end when we do OP return. So we essentially exit out of this entire thing. Oh boy. I'll really need to think about that, because I need to now restructure the way I do literally everything, right? Because since we, yeah, this is actually very cool. Since we type check and everything, when we revisit the same instruction, I don't need to have a special hack for while loops. I never thought about that. Wait a second, this is actually very cool, right? If I have a while loop, do body, I can just follow the control flow as usual and treat do as if, and I will naturally visit while again, and in a while I have the, oh my god, that means this is the right approach. It simplifies everything. I can now remove the hack of checking loops as procedures, because it will just come out naturally. Holy shit, I didn't realize that. Do you guys understand what I'm saying? Yeah, so it's so fucking cool. So there is no difference between just do and if now. The only difference is that if jumps forward and do, well, I mean, actually end of the while jumps backwards, yeah. It's so cool. So plus PTR plus, so just a second. Proc PTR plus. Fuck. I think it's in core. PTR plus. Yeah, there we go. So that's the difference between them. PTR plus takes pointer as the first argument and offset as the second one. Plus PTR takes the offset as the first argument and pointer as the second one. OMG, it could explain why are there no clothes hanging on your clothes rack. What exactly? I'm not sure. Are you ever going to support operator function overloading? Yes. Operator function overloading is going to be a crucial part of the design of this language, believe it or not. Think behind your back. Okay, I know, but what exactly explains the lack of the closing? I don't know. There is some clothes that I put there, it's just like I remove them every time I start streaming because I'm a little bit embarrassed. So I have a pile of stuff that I keep moving around between the rack, the bed, and the chair. You know, the usual pile of clothing that everyone has. I had that one too, and it's also... Anyway, so let's actually continue the stuff. Yeah, everyone has it's not a pile, it's the pile that keeps moving around your room, right? It's like a living blob that lives with you, right? It just moves around. So yeah, that's basically what it is. Okay, so let me go through like everything and just take a look at how we check stuff. So if so yeah, that's very cool. Context check program from. So this is where we split, right? So if you encounter if operation, you type check the if operation. You type check whether you have boolean on top of the stack. Then you go to the next instruction after if and you type check the program from there. Then you go back and you sort of backtrack and you check what's gonna happen if you skip over the body. Right, and that's how you continue like type checking everything, so that's fine. If star is the same, I would even say they're literally the same to the point that I can probably just do something like this, right, and remove one of these branches, but I'm not going to do that because I may accidentally introduce some sort of a bug. Else just always jumps in absolute way, and while jumps back, it always jumps back. When you go a procedure, it doesn't matter. Return. Return is a very interesting thing. Return is a very interesting thing. It denotes the end of this entire stuff, but it also means that we need to type check the end of the procedure, right? So what we have to do, type check outs, right? Type check outs. We have to provide the current stack, right? So do we have a stack? Yeah, we have a pointer to the stack. So here's the stack. Do we have outs? No, I don't think so. So we'll probably have to take the context. So, so we have stack IP. So from the context, we only grabbed IP and the stack. Right, so that means I'll have to do context, type context, outs pointer plus. Right, and that's what we expect in here, and on top of that I'll have to take IP, and there we go. So this is what we're doing here. So we type checking outs, and that's it. When we do a call, we just do that, nothing particularly special. OP call like, inlined, doesn't matter, all of that should just work. OP while is an interesting one. OP while is an interesting one, and I think now we just don't have to do anything, believe it or not. So here, when we go into OP while, we start treating it as a separate procedure. You see, we do a recursive call into type check program from, insinuating that it's a new procedure. In fact, it is not. So I can just like continue moving forward. And so this one basically skips. And then we go, that's a lot of hacks in here, that's a lot of hacks. So I suppose the easiest thing to do here is going to be just like true and continue. So if everything goes according to the plan, we don't need this code. That's what makes this shit cool. That's what makes it cool. And everything, if everything goes according to the plan, we can treat OP_do as just if. Hopefully everything goes according to the plan. Because right now it is not like that. Right, so there is a difference in here. Right, so as you can see, the else branch for OP_do just breaks, but for the if, it continues, and I think we just need to continue in here. Right, so this entire thing may fail spectacularly, but if it fails, I'm gonna fix that off screen. Right, so I did the stream, I explained the main idea anyway, so you guys know how I plan to check the port, so you can use that idea for your language. Right, so the point of the stream is to just document the type system that I want to implement, right? So, and I think I already documented it well, but on top of that, as a bonus, I may try to just implement it. Okay, so type checking already visited thing. And what's cool is that once we sort of reach this step, right, we already type check everything on OP return, right? We type checked everything on OP return, so we don't need this huge blob that we already adapted for the separate procedure. So I think we don't need this blob. All right. And here is, okay, here is the pretty cool thing. You guys remember how I said that I have an array of the type frames that I just keep allocating and allocating, right? So, and I build the tree out of pre-allocated nodes. You know how I free them? Initially, I planned that I'm gonna do reference counting, but then I noticed something interesting. Everything that is allocated, all of the nodes that are allocated while type checking a procedure are not needed ever after you finished type checking the procedure. So there's whatever you allocating in here is separate from whatever you're allocating in here, and it's actually never needed. So what do I do? At the beginning of type checking the procedure, I save the current amount of allocated nodes, like type frame pool count. I save that count. I just save that count at the beginning of this procedure, and then when I finish type checking the procedure, I just return that type count back to where it was. I'm basically rewinding all of the allocated type frame nodes. So I don't even need to do reference count, because I know that all of the type nodes that are allocated, they are not needed anymore. I just can throw them away in one swipe, which makes this memory management so much freaking easier. Yeah, it's TMP rewind approach, but TMP rewind actually rewinds bytes, but this rewinds fixed size nodes, which means that this sort of like a rewind memory allocation approach works for a variety of different datas, which is also a very interesting thing that I would like to explore. Right. So, and it's actually, there is a lot of complicated concepts in Porth, right? So the type checking especially, I think type checking is the most complicated thing in the entire language, and I do plan to write some sort of like a white paper or some sort of a write-up on this entire thing in a more formal way, right? And it's surprising that I can achieve all of that with such a simple tools in such a simple language. Yeah, it is a very interesting vote, because we're trying to speed up the type checking thing, and we're almost done, hopefully. So we're either done and we're gonna have a huge success, or we're gonna have a huge failure and I'm gonna go and curl in the corner and just cry, and then fix everything on the next day and make a short video about you know, how I fucked up, but this is how it's supposed to work. That's how it usually goes. It's either a huge success after 2 hours of works, or a huge failure and I just like fix everything afterwards. So so we're gonna see which one is that today. Alrighty, so here we visited already the node where we were, right? So what can I do in here? I can just like type check whatever we have. Let me see. But that also means, oof, does that copy? do we copy the type context? Oh shit, we copy. That's cool. Like every time we spawn a new thread, we actually copy the... It does make sense. Okay, I just wanted to make sure that it is like that. Unfortunately, we don't have a concept of passing by reference or by value. We just have a pointer, so we sort of emulate that by passing pointers. And I don't really remember what's passed by value, what's passed by reference. Just like in C, right? Porth is as crappy as C right now, but we're going to try to make it better. We can't make C better because it already has a standard. There's a lot of code bases and stuff like that. So you have to go through the huge process, but I control Porth. I can try to make it better. Not sure if I'll be able to. Edit the video and put the success part at the end of it regardless. I'm not a video editor, I'm a programmer. I'm sorry, I don't edit videos. I tried to edit videos, but I failed spectacularly. I just can't do that. I prefer to just do what I'm good at, writing code and being angry at people. So professional staller right here. I mean, I'm not stalling, I'm solving the problem in my head right now and also thinking about the next step by talking through everything. It's a part of the programming. Me just stalling, what you call stalling, is part of the process, okay? Anyway, I'm a little bit nervous, okay? So, because we're almost there. So the only thing we need to do is just like type check things here and that's it. And we're done. Proc type check, right. Type check expected oats. Right, oats. So here we have to provide this stack. Here is the stack. And the expected outputs are located in the snap. Type snap. Basically, type snap is a snapshot of the stack at that particular point of time. Right, for each individual instruction, we have a snapshot of its stack. Right. So, and if we visit instruction one more time, we have to compare the current state with the snapshot of what we already visited. And if there is a mismatch, that means there is a type error. So, and the way we can do that is because type stacks are very lightweight, because they're basically like a Git history. So that's why we are able to do that. So, all right, so this is a stack, pointer plus, and there we go. So, and then we have to use IP, and I suppose this is going to be IP. There we go, and I can just do that. So that means I can simply remove that. All right, so let me try to compile the entire thing. And well, it compiles, right? So we're using Bootstrap compiler, the compiler that is not busted, right? So we're using not busted version of the compiler. But can now the compiler recompile itself? I don't even know. So let's write a simple program, right? So now it should like at least try to do something, right? We're not gonna put everything. We're only gonna do 34, 35 plus print, right? So there's no standard library because it will try to type check standard library, and I don't want it to do right now. And let's try to just run the compiler and compile main.porth. Is it main.porth? I'm not sure. Okay. It compiled main.porth. The new type checking process didn't complain about new type porth, and type checking took this amount of time, which is probably fine, right? So if we take a look at the type checking with the previous compiler, it's actually faster. Right, but it's if it's a new compiler, right? If it's a new compiler, it's kind of hard to compare them. They're pretty like fast on such a small data. If I try to run this entire thing now, it prints 69. It works. Okay, so the new type checking works. If I try to, for example, do not do print, right? So I don't do any print. Is it gonna complain that I have you know, unhandled data? And it's actually using new diagnostic messages. It is using new diagnostic messages. It fucking works. Like, I didn't have this diagnostic message, such a short diagnostic message before. It freaking works. Okay, so that is very fucking cool. And you can have two of them now. All right, so this is very, very freaking cool. So this could be one of the streams where I actually have a success, like first try, but who knows? Okay, so, and we have some problem on the stack, of course. Okay. Unexpected data on a stack, expected boolean, unexpected type boolean, but expected integer. Huh. This is very freaking interesting. Okay, so let me try to understand what's going on then. So this is that stuff. Ooh. Ooh. So let me see. We have a pointer on the stack. Then we have integer after that. We have an integer after that. Then I do dupe 0, and that is really weird. Huh. At which point I have to do all of that stuff? That's very, very interesting. So I feel like it's something, I think this is the first if. No, it's not the first if. It's actually very far along in the library. It is very far along in the library, so that should be fine. So if I kind of rewrite this thing as that, so what stat returns? What stat returns? I think the semantic of the type checking might have been actually altered. It doesn't necessarily mean that this thing is wrong, is that it's kind of type checked differently now. I think that's what's going on here, but I'm not 100% sure. Right, so the semantic is slightly different now. So here is the return, and then I just have to return that. Yeah. So this is the false, and then we do all of that stuff. Okay, so if I try to do this thing, not enough arguments for the dupe, well, I just have to do ret. Okay. Expected type, unexpected type integer. Shit. Oh, I think this is the first time we have elses. I think that's what's going on. Right. No, it's not the first time we have elses. But yeah. It's kind of weird. Okay. So I'm gonna remove that. Is it the first if star? Let's actually check. Yeah, you're right. It is the first if star. All right, so that's cool. Thank you, thank you, thank you. So the problem is happening on if star. Storm. You're a genius, exactly. Let me actually trust you. Trust. So now you can send links. You can send malicious links in the chat, and the bot is not going to ban you, and you can grab everyone's IP. Don't do that. I'm joking, obviously. But anyway, that's cool. So there is a bug with if star, but so far everything's fine. So let's try to maybe play with this entire thing. So is it gonna be if 69 equals, we're gonna print nice puts and okay puts. Oh yeah, of course. You just can't do that. 69 print and 420 print. Print in intrinsic is still useful even after that code elimination. Okay, but if I change it to 35, it is totally fine. Right, and if I do some additional thing in here, it will say inherited data on the stack, and it's coming from... Holy fucking shit, that's cool. That's cool, that's cool, that's cool. Okay, it is actually checking all of the stuff. So we can try to do else. Alright, else. So it's 420, but if it's 34, it's gonna be that. Okay. If I get trusted, I know the first link I'm gonna set. Okay. There we go. So let's actually do the following thing. I'm gonna just do let like so. Monk.js. Yeah. It's too obvious. I mean, come on. It's like everyone knows this ID. Are you serious? Everyone knows this ID. Come on. You want to be sneaky? Google up. Search for Rickroll, but it never ends. Rickroll, but it never starts. I'm sorry, never starts. So it has a completely different link, and it's actually way more annoying than the original Rickroll because it literally never starts. Yeah, thank you so much. Yeah. Right, and yeah, it's kind of sad that my most popular thing, like I managed to achieve almost like unachievable 10 million views. 10 million views. Not for a cool programming language, not for a cool game, not for anything, but for a fucking shitpost. Ah! I hate internet. Suffering from success right here. And the funniest part is that since the video is copyrighted, I didn't get anything. And the channel is also demonetized. Yeah, I made that video. Yes, I made that video. I actually spent 2 hours editing that video perfectly, right? Just, you know, stitching the seams and stuff like that. It was kind of hard, to be fair. The internet rickrolled you. Yeah, exactly. That's what happened. The internet freaking rickrolled me. Okay, so we have something like return for 20 equals if star. Maybe we'll have to do something like else. We're gonna print for 20, and otherwise we're gonna just print 0, right? And is it going to do anything? Okay, so this kind of worked out, which is really strange, but okay, so for 20, okay, and then if I just do 0, 0, it will print. So this one works. This one works. That's really interesting. So let's try to ponder on the code that doesn't work, and maybe we'll be able to figure out the problem. Cannot reproduce. No, I can reproduce that. So that's kind of the problem. The problem is that I can reproduce that. And what exactly does it say? Unexpected boolean, but expected... Why would you expect this thing? So if I go here, we actually split in two. We either fall through and then visit this thing and just go into the next else, into the next else, or we jump in here. When do we visit? Okay, wait a second. This is actually very interesting. So this thing means that we visited this stuff twice. We visited this thing twice. Why would be... Oh, I see. I know what is going on. Okay. This is annoying. This is really annoying because it's kind of a quirk of the compiler. Okay, so essentially, if you hit any of the else's, let's actually, yeah, I know exactly what's going on, and it's just like, it's very annoying. Let's imagine the if-else chain, right? You have a condition, condition if, else, condition if star, and you have a bunch of these things. And then you have final else and final end, right? So if this condition is true, you fall through into the body, right? You fall through into the body, then you reach else, and else is supposed to jump to the end, or maybe to the value like after the end, or maybe to the end, doesn't really matter. So else is supposed to jump straight into the end. And here is the interesting thing. Right now it doesn't work like that. Else actually jumps to the next else. Seriously. Each else in this chain just jumps to the next else because it was easier to implement like that during the compilation. So because of that, you visit each else twice. The first time you visit it is through short-circuiting all of the else's, and the second time you visit it from the body itself. You literally visit it twice. So, and because of that, there could be some discrepancies that are allowed to happen between these visits, but they're not really correct. So first thing I'll have to do is to actually somehow during the compilation to not chain else's together, but basically make them all collapse into the same end, right? So they're not visited twice, if that makes any sense. So that's basically what needs to happen. And I wonder if I can easily implement that right now. So what's the easiest way to implement it right now? So end. I don't think I can, because that's like a lot of effort. We can make like an additional step after the compilation where we just go through all of these entire things, right? We just go through all of these entire things and we just collapse them together, right? But apart from that, I think this entire thing works. So let's actually take a look. Okay. Right, so this is probably something that I'm gonna do off screen, or maybe I'm gonna make a short video on like how I collapse these else's, right? So, but let's see if we achieved our goal, because our goal was to speed up the type checking of the like a lot of like ifs, right? So let's do something like maybe zero cast boolean, right? If end, and if you have like, you know, I don't know, 20 of those, right? So we have something like this. The type checking of that code is going to take enormous amount of time, right? So let's take a look. Yeah, there we go. So here's the problem that we were trying to fix, right? So if you have this thing, oh yeah, maybe it's too much actually, because it starts to grow exponentially. So the type checking is exponential, right? So what we have in here is just basically like exponential algorithm checking all of the possible paths, right? So it's gonna take some time. So I'm not sure, like maybe I actually put too many of these things, but yeah. So maybe it's too much. So I don't want it to be too long, because again, it's exponential, right? So, and I'm going to do 2 things in here. So yeah, this is precisely, this is what I showed at the beginning of the stream. So this is how type checking works, and it took 7 seconds on this very simple code, right? And if somewhere here we just put 10, it will find that 10. Oh, actually it found it very quickly. Yeah, it found it relatively quickly, right? If I put it in here, right? Yeah, so it just found it, but it was also type checking shit ton of different things. Might as well maybe put this thing in here, in else, and it still finds it really quick. Anyway, so now I'm gonna try to use the new compiler and see if the new compiler can do the same thing faster. Okay, so that's the entire type checking. But does it actually work? What if I put 10 in here? It found it. It found it. And in fact, it actually works, I think. So I can put like 69 print in here, right? So it doesn't compile because we have this thing that's not supposed to be here. And if I compile it, it should print 69 as usual. So there is some bug with chaining else's, but we changed the exponential type checking algorithm to a linear one. Right, because if we find the operation that we already visited, we don't continue type checking because we know it's snapshot of its types. So that's basically the stream for today. There's still one thing left, but I'm gonna do that like, you know, outside of the scope of today's stream. So, all right. Does anyone have any questions maybe about what we've done today? So we've done actually a pretty cool thing, I think. Right, so we're basically using a persistent data structure to constantly take snapshots of the type stacks, right, and compress the exponential algorithm into a linear one. That is so fucking cool. So freaking cool, I love that. So, does anyone have any questions? Chat. Just do what Swift does and throw a compiler error expression to complete. Does it do that? Really? Is that what it does? Oh, by the way, fun fact: the creator of Factor programming language, one of the another famous stack-based programming language, just like Joy, actually works on Swift. I heard rumors that he created this language when he was like a kid or something, when he was 14 or something like that, but I don't want to lie. So, but I heard rumors like that, that he was really, really young when he created this language, and now he works at Apple on Swift. But I don't know, actually. So. So, Dinosaur checks out. Yeah. Practical stack programming language. Yeah. So I'm gonna put that in the description. Factor programming language. There we go. We need a cool logo? No, we need a cool language. So. Hello, found your YouTube channel and been enjoying binging a lot of videos. First time watching live. Hello. Hello. I did. Alright, I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you on the next session. Maybe I'm gonna just make a short video where I implement the else if compressor, if that makes any sense, that avoids, you know, how to say that, like visiting else's twice, which creates this sort of weird error. But maybe it's not I think that's the error. It must be that error. Anyway, so I see you next time. Love you.